The dashboard clock reads to 14 a.m. outside. The Siberian taiga presses against the windshield like a wall of black. The temperature on the cab's interior gauge reads -40 degrees Fahrenheit, the same number as the temperature outside, because the engine died 40 minutes ago, and the heat has already gone with it. There is no other vehicle on the road. The nearest town is listed on the map as 212 kilometers to the east. The driver, a man named Alexei, 38 years old, 17 years of winter routes behind him, does what he has always done when the engine fails in deep cold. He pulls his heaviest winter jacket over his shoulders, zips it to the collar, and tells himself he will be fine until morning. He will not be fine. What happens to a human body inside a sealed metal box at -40 degrees? And why the things most drivers believe will save them are the precise reasons they do not survive, is what this investigation is about. By the time we reach the end of this route, you will know the 3 improvised heating methods that produce lethal concentrations of carbon monoxide in under 20 minutes. You will know the single engineering device that changed winter survival in Siberian trucking, and you will understand why Alexei's jacket was not his protection. It was his first mistake. Hit that subscribe button. This goes deeper than any documentary you've seen. Don't gamble on finding this again. There is a version of this story that gets told in truck stops along the R504, Kolyma Highway, the road that runs through the coldest permanently inhabited region on Earth. In that version, experience is the protection. You learn the cold. You respect it. You develop instincts. That version is not wrong, but it is dangerously incomplete because the physics of extreme cold does not negotiate with experience. It operates on timelines that ignore instinct entirely. What we know from incident reports, toxicology records, and thermal engineering data collected over decades of Siberian trucking tells a different story. It tells a story of drivers who did everything they were taught to do and died from the gap between folk knowledge and physics. This is not a story about recklessness. It is a story about the specific, measurable ways that common sense fails when the temperature drops below the point where human intuition was designed to operate. We will move through 7 stages of this investigation. The baseline conditions of a Siberian overnight stop, the physics of why passive insulation fails, the chemistry of why improvised heat kills, the engineering that finally solved the problem, the fuel and battery failures that arrive before the cold does, the correct way to build warmth against the body itself, and the protocol that gives a driver a chance when every system fails simultaneously. The first hard fact arrives in the next 60 seconds. At -40 degrees Fahrenheit, exposed metal contracts so violently that truck door seals crack open in under 6 minutes, and the heat stored in a diesel engine, block after shutdown, dissipates completely in less than 40. That is not an estimate. That is what thermal conductivity measurements on standard European and Russian-built long-haul cabs consistently show when tested at the temperature ranges common to the Yakutia region between November and March. Consider what that means in practical terms. You park the truck, you shut the engine. In the time it takes to eat a meal, the metal shell around you has become thermally identical to the environment outside it. The cab is no longer a shelter. It is a container. The same temperature as the taiga, the same temperature as the road surface, the same temperature as the air that, at -40, causes exposed skin to develop frostbite in under 10 minutes. The standard response to this, the one that has governed Siberian trucking practice for generations, is to leave the engine running. Keep the heating system active. Never let the block cool. This is not a myth. It is a real solution. But it is also a solution that carries a cost that most drivers either underestimate or choose not to think about carefully. A diesel engine idling through an 8-hour night burns between 2 and 4 liters of fuel per hour, depending on load and age of the unit. That is up to 32 liters to survive a single night parked on a multi-day route through eastern Siberia, where fuel stops can be separated by distances that take 12 hours to cover. That calculation becomes a survival threat of its own kind. But the fuel cost is not the most dangerous part of continuous idling. The dangerous part is the exhaust systems on aging trucks and a significant portion of the long-haul fleet. Operating on Russian Federation roads east of the Urals consists of vehicles more than 15 years old, developed microfractures and corrosion failures in their joints and manifolds. Under normal driving conditions, these failures are invisible. The vehicle moves, air flows, exhaust disperses, but when the truck is parked and idling in windless, sub-zero conditions, carbon monoxide from a compromised exhaust system can migrate back along the undercarriage and enter the cab through door seal gaps that the cold has already cracked open. The irony here is precise. The very cold that forces the engine to keep running also opens the pathways through which the engine's exhaust kills the driver. Russian transport safety data compiled by the Federal Road Agency across multiple winter seasons lists engine idling as a documented contributing factor in carbon monoxide fatalities among long-haul drivers. Not as the primary cause, but as the environmental condition that made the primary cause possible. That distinction matters. It means the problem is not idling itself. The problem is idling in a vehicle with compromised seals, in cold that expands those compromises, without a detection system that can tell the driver the air is no longer safe. If keeping the engine running is dangerous, and turning it off is fatal, what exactly are drivers doing between those two options? The answer, it turns out, begins with the things they reach for first. And those things are where the real danger lives. A thermal sleeping bag rated to -20 degrees Fahrenheit will not save you at -40 because the bag is not the problem. The air inside the cab is. This is the first myth that winter trucking culture has never fully corrected because it feels wrong. The sleeping bag is warm. You can feel it. You zip it up, and the immediate sensation is of warmth returning. What you cannot feel is the rate at which that warmth is being drawn out of the enclosed airspace around you, through the metal walls, through the cracked door seals, through the windshield glass, by a temperature differential so extreme that no passive insulation system, rated for recreational or military camping use, was designed to counter it. Here's the physics in plain terms. Insulation works by slowing the transfer of heat. The greater the temperature difference between inside and outside, the faster heat moves through any given insulating material. A sleeping bag rated to -20 degrees assumes a starting interior temperature, the heat of the human body, radiating into a contained space that, in a cab that has already cooled to the ambient exterior temperature, does not exist. You are not warming a space. You are trying to generate enough heat with one human body to overcome a differential of 80 degrees Fahrenheit between your skin and the metal surrounding you. That is not what sleeping bags are built to do. Stop and translate that into physical reality. A single adult human body at rest generates approximately 80 watts of heat, roughly equivalent to a standard incandescent light bulb from the 1970s. The metal shell of a truck cab at -40 is pulling heat away from you at a rate that your body cannot match. The bag slows that loss. It does not stop it. Without a supplemental heat source, the interior temperature of the cab will reach lethal hypothermia thresholds for an adult within 3 to 5 hours. This is the point at which drivers make the decision that kills them. The improvised heat sources that appear at this decision point, portable propane or butane camp stoves, burning charcoal bricks brought from the cargo hold, household electric space heaters run through an inverter off the truck's battery, share one critical property. They are all combustion-based or thermally inefficient in ways that, in a sealed cab, become immediately dangerous. Carbon monoxide, the colorless, odorless gas, produced by incomplete combustion of carbon-based fuels, binds to hemoglobin in the human bloodstream at a rate approximately 240 times greater than oxygen. That ratio is not a metaphor for danger. It is a chemical displacement equation. In an enclosed space with limited fresh air, a single portable camp stove burning propane produces enough carbon monoxide to reach the O-SHA-defined immediately dangerous to life and health concentration, parts per million, in under 20 minutes. You will not smell it. You will not see it. What you will experience, if you experience anything at all before unconsciousness, is a mild headache and a sensation of unusual drowsiness, at which point the decision you need to make to survive has already been taken from you. Toxicology reports from cold weather vehicular deaths in both Russia and Alaska show a consistent pattern. The presence of elevated carboxyhemaglan carbon monoxide bonded to red blood cells in drivers found deceased in parked vehicles with improvised heating sources. Not occasionally. Consistently. The improvised heat source is not an emergency backup. It is a documented mechanism of death in the specific environment of a sealed truck cab. The question that emerges from this pattern is the one engineers eventually had to answer. How do you generate heat inside a sealed cabin using combustion without allowing the products of that combustion anywhere near the air the driver breathes? The Webasto auxiliary heater burns diesel fuel at a rate of between 0.1 and 0.3 liters per hour. Less than fills a standard coffee mug and produces enough thermal output to maintain a truck cabin at 65 degrees Fahrenheit through an 8-hour Siberian night without engaging the main engine once. That figure deserves a moment. The engine idling solution burns up to 32 liters through the same night. The auxiliary heater burns between 0.8 and 2.4 liters. The difference is not incremental. It is the difference between a strategy that depletes the fuel reserve needed to complete the route and a strategy that barely registers on the gauge. But the fuel efficiency is not what makes the auxiliary heater the engineering solution to the survival problem. What makes it the solution is the isolate combustion chamber. Here is the principle. In a standard engine running inside a vehicle, the combustion occurs in the engine block. The exhaust exits through the exhaust system, and the cabin air is heated by a separate loop that pulls warmth from the coolant, never from the combustion gases directly. The system works because the engine was designed with that separation as a fundamental requirement. What auxiliary heaters like the Webasto and its German competitor, the Webasto, replicate is precisely that separation in a unit the size of a large shoebox. Mounted externally on the cab frame, the device draws air from outside the cab for combustion. It burns a small quantity of diesel in a sealed chamber. The combustion gases exit through a dedicated exhaust port that terminates outside the vehicle completely, isolated from the cabin air supply. The heat generated by combustion warms a heat exchanger. The heat exchanger warms cabin air drawn through a separate intake. The driver breathes air that has never been in contact with combustion at any point in its path. The electrical draw at steady-state operation is approximately 10 watts. Consider that number. 10 watts is the power consumption of a single LED nightlight. The auxiliary heater maintains a survivable interior temperature in a metal box at -40 degrees Fahrenheit while drawing less electricity than the lights you leave on in the hallway when you go to sleep. The engineering principle underlying this system is not novel. Isolated combustion chambers with separate exhaust routing are standard in marine heating systems, in aircraft cabin heating units, and as engineers at both Webasto and Webasto have noted in technical literature, in early NASA Habitat thermal management designs developed during the space program of the night. A truck driver sleeping on the Kolyma route in January is resting inside the same basic thermal logic that kept early astronauts from freezing in test facilities in Houston. The irony, noted without drama, is this. The technology that solves the problem has existed in commercial form since the 1950s. The fatalities continued for decades after it became available, because adoption across the Russian long-haul fleet has been uneven, cost-dependent, and in many cases, simply unknown to the drivers who needed it most. But the most unsettling part is still ahead, because the auxiliary heater only works if the fuel reaches it, and at -40, diesel fuel stops behaving like a liquid at -40. Standard diesel fuel begins crystallizing into a gel that clogs fuel filters and fuel lines in under 2 hours, a process called paraffin crystallization, or fuel gelling, that most drivers only encounter after it has already stopped the engine and disabled the heating system simultaneously. Diesel fuel is not a simple substance. It is a mixture of hydrocarbon chains of varying lengths, and the longer chains, the paraffin waxes begin to solidify and clump at temperatures well above what most American drivers associate with cold weather fuel problems. Standard number 2 diesel, the fuel used in most American and European trucking operations, begins showing paraffin crystallization at around 14 degrees Fahrenheit. At -40, it does not gel gradually. It thickens to the consistency of petroleum jelly and stops flowing through the fine mesh of a fuel filter within a time frame measured in minutes, not hours. The solutions used by experienced Siberian truckers operate at multiple points in this process. Fuel additives, specifically kerosene, blended directly into the diesel tank at ratios of between 20 and 30% lower. The point at which crystallization begins by depressing the freezing curve of the mixture. Arctic-grade diesel, formulateth with shorter hydrocarbon chains, is used on routes where standard fuel is unavailable. Fuel tank heaters, which are often integrated into the same auxiliary power unit as the cabin heater, maintain the fuel temperature above the crystallization threshold throughout the night. The battery problem is related but distinct. At -40, a standard lead-acid truck battery loses between 40 and 60% of its rated cranking capacity. The battery has not discharged. The chemistry is intact, but the electrochemical reactions that produce current slow dramatically in deep cold, and the remaining capacity is often insufficient to start the engine against the increased viscosity of cold engine oil. This is the scenario in which a driver wakes to a working heater, a full fuel tank, and an engine that will not turn over because the battery that was adequate at 32 degrees has become inadequate at -40. The fix is not complicated, but it requires preparation that happens before the truck stops for the night. Battery blankets, resistive heating pads wrapped around the battery housing and connected to the auxiliary power system maintain battery temperature through the night. Dual battery configurations with one bank kept warm provide starting redundancy. On routes where these preparations were not made, the morning start failure is the beginning of the emergency, not the end of it. And when the emergency arrives, when the engine is dead, the heater has failed, the fuel has gelled, and the nearest help is 200 kilometers away. What remains is the protocol. The emergency survival sequence used by experienced Siberian truckers is not improvised. It is a specific sequence of actions designed to extend survivable time in a cooling cab until rescue arrives or conditions change. The mylar emergency blanket, the thin, reflective film developed originally for NASA spacecraft thermal control, reflects approximately 90% of radiated body heat back toward the body, creating a microenvironment that slows heat loss dramatically compared to conventional blankets of 10 times the bulk. One mylar blanket, properly deployed, can extend survivable time in a cooling cab by several hours. It weighs less than 2 ounces. The emergency candle, a single standard household candle burning in a metal container, produces approximately 80 BTUs of heat per hour. That is not enough to warm the cab. It is enough to prevent the temperature from dropping as fast as it otherwise would, buying time. Carbon monoxide detection in this scenario is mandatory because a candle burning in a sealed space will produce CO at lower but still meaningful concentrations over time. Deco Detector, a device that costs less than $30 and fits in a jacket pocket, is the instrument that tells you when to crack a window despite the cold. The sequence exists because the alternative, improvising under cognitive impairment from early-stage hypothermia, which begins affecting decision-making at a core body temperature only 2 degrees below normal, is not a viable survival strategy. Hypothermia does not announce itself clearly. It produces a sensation of warmth, a reduction in the urgency to act, and a gradual narrowing of the cognitive field that makes it increasingly difficult to execute the precise steps that survival requires. The protocol works because it was written before the cold arrived. What the Siberian trucking survival problem reveals, when examined from the outside, is a collision between two different kinds of knowledge operating on the same body in the same metal box. The first kind of knowledge is experiential, accumulated over years of winter routes, shaped by what has worked before, calibrated to conditions that fall within the range of what a human nervous system can perceive directly. This knowledge is real and valuable. It is also systematically wrong in a specific category of conditions, the category where the physical processes at work are invisible, odorless, and faster than the feedback loop of experience. Carbon monoxide poisoning is the clearest example. The gas produces no sensory signal at concentrations that are already lethal on a 30-minute timescale. The driver who has survived 5 winters by burning a camp stove in the cab has not learned that the stove is safe. He has learned that he has been lucky. The distinction is invisible to experience, but absolute in chemistry. The gap between experiential knowledge and physical reality in extreme environments is not unique to Siberian trucking. It is the same gap that produces avalanche fatalities among experienced backcountry skiers, drownings among strong swimmers in cold water, and altitude sickness in climbers who have summited lower peaks successfully. The human nervous system is calibrated for the range of conditions in which most human evolution occurred. Below -40 degrees, above 8,000 meters, in water below 50 degrees Fahrenheit, the calibration fails, not occasionally, systematically. What auxiliary heater adoption in Siberian trucking represents, in this broader frame, is the replacement of calibration-dependent survival with engineering-dependent survival. The device does not rely on the driver's ability to detect a problem before it becomes fatal. It removes the problem from the detection requirement entirely. The combustion never enters the cabin air. The driver does not need to smell what is not there. The re-engagement question that this analysis raises is not technical. It is social. If the technology that solves the problem has been commercially available since the 1950s, and if the fatality pattern it addresses has been consistent for decades, why does adoption remain incomplete across the fleets operating in the regions where the need is highest? The answer points to a failure not of engineering but of information distribution. The same failure that keeps the blanket out of the cab of a driver who has spent $3,000 on cold weather. Gearbut has never been told that 2 ounces of reflective film outperforms all of it in a static thermal emergency. Knowledge, in extreme environments, is not background. It is load-bearing structure. Every layer of protection covered in this investigation, the auxiliary heater, the fuel additive, the battery blanket, the mylar film, the CO detector, the emergency protocol, is a precisely engineered distance between a human body and a physics that operates without reference to effort, experience, or intention. The cold does not evaluate how many winters the driver has seen. It applies the same equations to every cab, every night, at every temperature below the point where unassisted human biology can hold the line. What this reveals is not a story about Siberia. It is a story about the specific, recurring human tendency to trust the knowledge that came from surviving previous versions of a problem, and to underestimate how precisely different the current version might be. The driver who survives for winters using a camp stove has not been proven right. He has been given 4 more opportunities to be proven wrong. Picture the truck parked somewhere on the Kolyma route at 3 in the morning. The taiga is absolute in every direction. The temperature is -40. Inside the cab, a device the size of a shoebox draws 10 watts of electricity and burns less fuel than a coffee cup to keep one man warm until sunrise. Between the man and the physics pressing in from every direction, there is nothing dramatic. There is only precision. In the coldest places, survival is always an engineering problem. We're 1 layer deeper than when we started. Subscribe and follow this investigation wherever it leads.